segment so that you guys and the people who are missing this can maybe catch up by listening. I can put this up somewhere. Um, okay, so are there any, is this um, clear so far, or we'll have to have you do some exercises so you understand what's going on. The regex exercises ask you to sort of identify maps, whether they're one-to-one, onto, stuff like that. Um, and oh, Christian, hi. I have been recording the what you missed. So the first 30 minutes or so um, has been recorded so far. So you can catch up later when I put that up. But we're talking about maps, and we've just defined the ideas of um, one-to-one maps and onto maps. And oh, there's a name. We're going to call a correspondence is a map that is one-to-one and onto. Okay, so there's those two properties, the correspondence, and then um, each of these properties, one-to-one has a formal definition here as a conditional. Or this one isn't quite a conditional. It says there's that, but you can use these formal definitions to prove various properties of compositions of maps um, down here. And um, they all, because any map can be represented with a matrix, and because matrix compositions are represented by matrix products, that's where the matrix product come in. All those properties of matrix products that we had also have to be properties of compositions of maps. So for example, it's going to turn out that if I compose 3 maps, first G and H and then F, that's going to be the same map as if I compose the other two and then the third. So that's an associative property. And so if I represented like this F with a matrix, this with a matrix, this with the matrix that represents the composed map will be the product of these matrices. And we haven't gotten to this yet, but I'm just sort of telling you what's coming so that you can sort of see why we're introducing these ideas. Then you can see that because matrix products are associative, that corresponds happily to the fact that compositions of maps are also associative. Okay. And this is all in this tutorial at the end of chapter 5, just this idea for maps, the idea of a correspondence, one-to-oneness, onto-ness, composition, and the idea of a map. So that's just the basics, the basic ideas behind the scenes. And then we come to the notion of linear maps, which is back to linear algebra. So at this point, all you may need to do from this is understand the idea of composition and be able to identify whether maps are one-to-one or onto. So are there any questions before we move on to doing the linear part of maps?
No.
Okay. Well, probably when we get to some questions, to some actual problems, that will, hopefully there'll be some questions. Okay, so a linear map, the idea of, well, first of all, what we have here is we have a map between vector spaces. So we have, say, V and W as 2 vector spaces. And they're not, say the map, let's call it M here. So again, the map takes to every vector in the domain it assigns a partner in the codomain. That's what the map is, this assignment, this pairing. Um, so every vector here goes to some vector W in here. And we use this, the functional notation. So we'll say like W of V equals M of V, sorry about that. The map takes the vector V to the vector W, and that's, so this notation is taken from the functional notation that you know, like f of x equals 2x. So the words here, f of x, you would use that here, m of v, for the okay. So this is a map, but not every map is a linear map. And the linear maps respect the linear structure of the vector spaces, in the sense that over here, if I have, say, V1 and V2, well, since the map assigns there's going to be a W1 and a W2, W1 is M of the image. We'll also say that W's, we also say this is the image of V. So you can say that the image of V is W, meaning the map assigns the partner of V is W. So W1, if I have a V1 here, there's going to be a W1 that's the image of V1, and there's going to be a W2 that's the image of V2. So given any two vectors in the domain, you can then form the linear combination of those two, and then ask, how does the map act on a linear combination? In other words, can we express it in some sense in terms of these two things, or does it produce something that's different? Well, a map is, the linear property is the linear combinations go to linear combinations. So this has to equal A M of V1 plus B M of V2. So so the image of a linear combination is the same linear combination of the images. That is, that you've got the same coefficients. So um, this is the linear property, and it's very restrictive on the kind of maps that you have, and that's what makes all this stuff, like, it makes all this stuff work, because you need this property, and when you do that, a lot of nice things happen. Okay, so this is some consequences of this. This is equivalent to two simpler properties. Let's say that B equals 0 here. Well, this goes away and that goes away. So this says that M of AV1 has to equal A M of V1. And this is true for any vector V1. So if I scale so that the rescaled version of M1 has to go to this, like if this is this, if I take M of 2V1, that has to equal 2M of V1. So the map has to be linear, the map has to have this property. But it can also, the other case, the other special case is A equals B equals 1, in which M of V1 plus V2 equals M of V1 plus M of V2. So the image of the sum is the sum of the images. So these two properties are equivalent to this property here. So this is version 1 of the linear property. This is version 2, and they're equivalent. If I know both of these for any number a here, if I know both of these, then I can prove the linear property. If I know the linear property, as we just said, these properties are just special cases, and I can if I know these, then I can do the same thing that I can reproduce this formula up here. Okay, well, that's the linear property. Now, the linear property, the map might be linear, and all the maps we look at are linear, but it may be onto or not. And it may be one-to-one or not. So it might have these properties or it might not have these properties. So you can have linear maps that are onto and one-to-one, linear maps that are onto but not one-to-one, linear maps that are one-to-one but not onto. And these conditions are a little bit more complicated than in the cases we looked at with these finite domains here, because here the things were simple because we only had a finite number, 3 elements in each set. But here we have in vector spaces an infinite number of elements. So the consequences of being one-to-one or onto are somewhat more, they're more serious, and they're a little bit more involved to see what's coming about. Now, the first, there's 2 special cases. One is which you have, and that's what the chapter starts with. It starts with correspondences. Correspondences are linear maps that are onto and one-to-one. Okay, let me